자, 시간이 되었으니 시작하겠습니다. 더블 만들고 에틸렌이고 HCl이야. 그리고 HCl이야. 어디션 일어나겠죠? 프로톤 핵심은 바뀌고 카보페라가 생긴 자리에 CL 마이너스가 들어가가지고 어디션이 일어나고요. 그죠? 에틸렌의 CL2 또 어디션 일어날 거야. 파일렉트론이 먼저 지게 CL을 반으로 쪼개가지고 CL 플러스가 먼저 들어가고 또 카보페라는 생기고 CL 마이너스가 돌아와서 CL 두 배 들어가는 어디션 되는 거죠. 벤젠의 CL2 벤젠의 자, 들어가는데 CL 플러스가 먼저 와서 붙고 그 다음 반응은 플러스가 생성된 자리에 CL이 또 못 들어갔지. 그거를 프로톤이 나가면서 그 차지를 받고 사라졌어요. 그죠? 그래서 결론적으로는 치환 반응이 일어나는 거죠. CL이 하나 들어가고 프로톤이 하나 빠지고 그게 일렉트로피릭 서스티션이라고 배웁니다. 벤젠의 HCl 제가 노 리액션이라고 써줬습니다. 다 맞출 것 같아가지고 이런 말을 만들었는데 벤젠의 HCl을 집어넣으면 첫 번째는 파 일렉트론 도네이션에서 프로톤 캡처를 보고 그러면 파지티브 차지가 생겼는데 그 다음엔 네가티브 차지가 되게 들어올 수는 없잖아. 아로마티스를 회복해야 되니까. 그 결국은 작은 프로톤을 도로 내놓거나 옆에 있던 프로톤을 내놓거나 해서 프로톤을 캡처했다 프로톤을 도로 내놓는 시험 문제 내면서 너무 수업 시간에 한 대로만 내가지고 다들 다 걱정받으면 어떡하지 그랬는데 잘 쓴 친구들 중에도 가끔 이걸 반응이 일어난 것처럼 쓰는 경우가 있더라고요. 벤젠은 이게 의사들이 처음 의사들은 이게 막 신기한 병에 대해서 막 배우잖아요. 이 병의 증상은 열이 39도가 나고 머리가 아프고 뭐 이런 얘기들을 막 해. 새로운 환자를 딱 보면 막 100만 명 중에 한 명밖에 안 일어날 것 같은 이상한 병 이름을 막 들이대고 그래. 이 반응이 막 일어나는 거 들여다보다 보면 이렇게 막 아무거나 갖다 놓으면 벤젠에다가 산 집어넣는데 막 반응이 일어나. 벤젠은 명패잖아요. 일반적으로 잘 안 일어나는 반응이겠지. 그러니까 이런 밸런스를 이제 조금씩 있게 가야 될 텐데 그래서 메커니즘으로 보면은 왜 어떤 건 되고 어떤 건 안 됐을까 하는 이 부분을 할 수 있으면 기본을 생각해보자는 거죠. 파이반드가 있으면 일렉트론을 도네이팅 하려는 프로퍼티가 크다고 배웠고 그것 때문에 파지티브 차지를 들고 있으면 그거 먼저 캡처하는 프로퍼티가 있었고 일렉트론 움직이는 걸 보면 더블반드가 있는데 엘리미네이션이 잘 안 일어날 거고 이렇게 더블반드가 있으면 보통은 어디션이 일어나죠. 하나 주고 나면 나머지 하나로 들어가가지고 엘리미네이션도 일어날 수도 있어. 이번 같은 거. 그런데 이렇게만 썼으니까 옆에 다른 지연기가 없다고 가정하면 그런 거로 어디션이 더 많이 일어날 거고 파일 일렉트론이 있으면 그건 일렉트론 주는 효과가 더 클 거다. 그죠? 현재도 마찬가지로 우리가 배웠던 반응에서는 일렉트로필릭스 액티션을 배웠으니까 1차적으로 일어나는 이런 파일 일렉트론을 주는 효과 때문에 반응이 시작된 거죠. 그런데 그게 그 어디션으로 가지는 못했고 바로 테스트를 회복하기 위해서 파지티브 차지 생긴 거를 프로톤을 버림으로써 생겼기 때문에 서브스티션이 일어났고 그랬던 거죠. 자, 이게 지금까지 배웠던 거에 대한 대충의 선언으로 좀 그리고 우리가 이제 새로운 토픽으로 들어가게 되는데 퍼즐로만 보면 되게 대단히 비슷해 보여야 되는 카본 더블 반드하고 카본 악시즌 더블 반드가 왜 차이가 날까? 이런 걸 보기 시작하는 거예요. 카본 더블 반드에서는 일렉트론이 남아돌기 때문에 줄려고 했고 두 개 시메트릭했기 때문에 한쪽에 쏠리고 있지 않고 그랬는데 카본 악시즌 더블 반드가 되면 그래도 우리가 배우기 시작한 거고 일렉트론이 이쪽으로 치우치게 되고 그러면 카본 사이트는 일렉트론이 부족하고 일렉트론이 부족하기 때문에 일렉트론을 받아들이려는 경향이 커질 거고 카본 사이트는 일렉트론을 받아들인다 하고 일렉트론을 좋아한다는 게 일렉트로필릭하다 그렇게 표현했던 거죠. 그런 프로퍼티들을 오늘 배우기 시작하겠습니다. 오늘 누가 1등인가? 혜린이 어디서? 이야 축하합니다. 오늘 동전이 다른 동전이에요. 자, 시험 하나 we just finished the first division and then move to the second part. So these are all 5 chapters we are going to study from now on. These are all about the CO double bond. So organic chemistry in a sense as the Lego building blocks is quite simple. Carbon, hydrogen, oxygen, CO single bond we have learned. Alcohol, ether, epoxide, kind of thing we have learned. Now we move to carbon, oxygen, double bond. Then there are so many things we need to talk about. 그렇게 많지는 않아. 그런데 그것들이 어떻게 연관되어 있고 어떻게 비례를 하는지를 잘 이해하는 게 오르가닉 케미스트리를 이해하는 기본이 되는 것입니다. I changed the coin. You can guess which year this coin was made. Last time it was 2021. Right? This was the 1 year before. 2020. 매년 만드는데도 이 퀄리티가 조금씩 다른데 2020년에 만든 게 좀 더 퀄리티가 나아요. 오늘부터는 2020년도 줄 테니까 이미 받아간 친구들도 또 새로운 거를 수집할 기회를 계속 설명해 주길 바래요. Okay, so we start the chapter of Aldehyde Ketone. CO double bond is very commonly discovered in nature. So as you can see here, now steroid molecule, carbon, hydrogen, and carbon, oxygen, single bond. Now there's a time to time you can see CO double bond there. And here, nitrogen we didn't touch seriously yet. That's almost the last chapter. And then phosphorus a little, but we are not going to touch too much about that. So carbon, oxygen, double bond we are going to study. If you wanted to make it, then maybe we can start with already we learned about the carbon, oxygen, single bond, the alcohol. So maybe we can start with the alcohol. If we need a lot, then maybe some catalyst. may not be the common reaction in organic chemistry textbook, a little more engineering or chemical engineering size of tons of the material could be synthesized by very, very carefully engineering wise the optimized conditions. So to make the one carbon alcohol, we call it methanol, and then if it forms this the oxidized form, what's the name of this? 뭐 다 아는 건데 얘기해줘. Formaldehyde. Okay. And if is two carbon is attached to here, then if this is oxidized, then this can generate acetone. So this kind of the material, the one idea can be maybe by oxidizing alcohol, we can make the ketone or aldehyde. So let's check the nomenclature. Nomenclature means the naming. Right? The formal naming is nomenclature. So let's just start with the alcohol. Okay, how do you give the name of this alcohol? Alcohol we can call methyl alcohol, ethyl alcohol, but that's a common name. It's not systematic name. It's not UPET name. Right? So as a systematic name of this, and we decide the longest chain and give the numbering as oxygen as the lower number. So 1, 2, 3, 4, 5, pentane, pentanol. And with the numbering here, 2-pentanol. And there is a substituency here, 2-methyl, 2-pentanol. So in your textbook it says 2-methyl, 2-pentanol. Now to make it a little more looks like a formal, maybe this is the recent definition. That's called 2-methyl propan 2-ol. It doesn't matter. Even though you change the rule and different people use a different name system anyway in the literature. At least you can give reasonably systematic name and you can understand what is the structure that is good enough for fun. Either name you use, I will give you the full credit. How about this? Backbone is the cyclohexane. It has a 2 alcohol, so hexane diol. Position wise, it helps you, right? Position I said 1 and 4. 1,4 diol. Cyclohexane 1,4 diol. And it has a stereochemical property here too. It can be 2 different isomers. One is trans and one is cis. Then you should provide all the information. Then there's a name can be cis 1,4 cyclohexane diol. They recommend cis cyclohexane 1,4 diol. Okay. How about this? Now the longest chain up to here is helping you with the naming. Seems like alcohol is a higher priority, so it has a lower numbering. So 2, 1, 2, 3, 4, butane, 2-butanol, or butan 2-ol. Okay. And there is substituency here. This substituents what we call benzene, phenyl. Okay, benzene is here, CH2, added one is the benzene. So this one is 3-phenyl butan 2-ol or 3-phenyl 2-butan. Okay, so this is review of the alcohol naming. Then if you move to aldehyde, alcohol we put OL. Aldehyde, similar way we can put AL, aldehyde R at the end. Okay. Then if it's a 2 carbon, we call it ethanol. Then 2 carbon, the aldehyde, how do you like to go? May not be very familiar to you, but official name is ethanol. Is the systematic name. Of course, we have a more common name, acetaldehyde, usually we use, but systematic name was ethanol. How about 3 of them? 3 carbon, propanol, then propanol. A little more complicated one. Now we have aldehyde here. Again, aldehyde has the lowest number, and longest chain is this chain, 5 more. Pentane, pentanol. Aldehyde is always at the end, right? One position. Then pentanol. Then we can give the numbering 1-methyl, 1-ethyl. which one comes first? Ethyl because alphabetical order. So now giving the numbering 2 ethyl, 4 methyl pentanol. Here, why don't you call 1 pentanol? Even though you put the 1 pentanol, it's not wrong answer, but that's redundant. Means it's not necessary. Aldehyde is always at the end. If it's in the middle, that's a ketone, not aldehyde. That's why if you put 1 extra, that's why you call legs of a snake. Right? 사조. 없어도 되는데 의미가 통하는데 굳이 넣어서 봐줄 수도 있고 페널티를 먹을 수도 있고. In this case, the safest option is pentanol. Okay. Now, common names. This compound, what do you call? 수업을 듣는다고 생각하고 그냥 시시한 질문들 답을 해줘. 하나, what's this name? 수업 누가 쓰다고 하는데 benzylaldehyde. Okay? So some of those the reagent name we have a systematic name like this, but very common the long history names still we use. So first one, formaldehyde. What is the second one? Joey, what's the second one? 몰라? 진짜 몰라? 어려운데. If we oxidize this, we call it acetic acid. Then this one, acetaldehyde. Okay. And third one, this will be a little difficult. Acrylene. And next one, even I don't know the name. So that means this has been quite long history one, but not very commonly used. If I do not know, then it may not be necessary. But this one is benzylaldehyde. Benzylaldehyde, acrylene. So here the structure was a C O double bond, and then this is called acryl. Acryl is quite commonly heard. So official name for this systematic name is methanol, ethanol, propinol because of this the alkene in, and benzaldehyde. If it takes out the benzene, carbaldehyde. This is the official name, but if you can know the common name here, that would be quite helpful for communication. So people still use this more than this the two systematic. Now, ketones naming. Alcohol and with O. Aldehyde and with R. Okay. Then ketone and with on. Is it ON or ONE? It's always confusing. It's ONE we call. Okay. Now here with this structure, 6 carbon, hexane. Then 3 hexanone. Or hexane 3 on. How about this? Now we have in and on together. In on together, which means with the priority, seems like CO double bond wins. That's why this has a 2. Now this one has 1, 2. Okay. So numbering wise, oxygen is higher and CO double bond is higher than single oxygen. So here, the aldehyde, this is 2 position. And then, how many carbon? 1, 2, 3, 4, 5, 6. Hexanone. 2 hexanone. And we needed to give this in position. So 4 hex first. Hex 4 in. 1, 2, 3, 4. 4 in, 2 on. A little complicated, but a little practice we can get. Last one here, you have a 2 on, and we can call this diol-dione. Position wise, 2 position, 4 position, hexane 2,4-dione or 2,4-hexadione. Okay. 조금 복잡하지만 연습하면 못할 정도는 아니겠지만 Common names. This one, acetone. Anybody knows the name of this? Yeah, acetophenone. 기분이다. And this one is a benzophenone. Now there is no systematic structure here. Aceto usually means this is aceto, this much, or acetyl. Phenone, well, phenone, benzophenone. Now the system doesn't work here. It's just a common habit. We have used it for a long time. Benzophenone, acetophenone, acetone. And it's acetone, you may know. Some of you did not put the answer for acetone reaction. 설마 아세톤 구조를 몰라서 안 쓰면 아니겠지. 안 쓴 친구가 있더라고. 이 정도는 알면 좋겠지. 벤젠, 아세토페논, 벤조펜. Okay, as the group, if you have just an R group, we call alkyl group. Okay? Alkyl. Now, if this is R with a CO together, what do you call? Acyl. We call this acyl group. And one benzene ring, phenyl. Benzene CH2, benzyl. And this one, double bond and vinyl. One more carbon. This is allyl. Okay. 페닐 벤질과 마찬가지로 헷갈리면 안 되지. This is acetyl. Okay. Acetaldehyde, acetic acid, acetyl. And with this, the CH3 with the proton, and this was formic formaldehyde or formic acid, and this one, formyl. Okay. And this one, benzoyl. Benzyl, benzoyl is different. Benzyl is without this oxygen, that's benzyl. Okay. With carbonyl, that's called as a benzoyl. 지금부터는 이 이름들을 여러분들이 안다고 가정하고 어느 정도 그냥 주고 갈 테니까 이 정도는 이렇게 두면 좋을 거야. Okay, naming one more. Here, ketone and aldehyde together. Then aldehyde was R. Ketone was on. How should we handle this? R on R. That's a little complicated. So in this case, the rule is we take aldehyde as a priority because this is always at the end. So numbering wise, this is also wins the number one position. Then how many carbon there? 6 carbon. Hexamer. If you want to hexamer, then somehow you should describe this. Right? This was added from outside, attached to the carbon, and that position we call oxo. So position-wise, 1, 2, 3 position, oxygen is added as a double bond. If this is alcohol, then we have different naming. But if this is ketone, just oxygen is added, then we call that position 3 oxo hexamer. Again, we don't use 1. Aldehyde is always one position is at the end. Right? So oxo, then later we are going to learn with the amine group, the nitrogen group. Then we have a little different naming there. So for now, for oxygen version, we call it oxo. There are some numbers of rules. That means you need to practice. Okay? So this is the problems in your textbook. So you are self-study. You try to give the name of this compound and also from the name try to redraw the compound structure. Okay? Okay, now moving to the chemistry part. How do you prepare for the aldehyde and ketone? Obvious, the first option is starting from alcohol and oxidizing. And what reagent do you need this? That's Martin. At least starting from primary alcohol, we want to start the reaction in aldehyde stage. That's what we have just studied. Even though you may not be able to draw the reagent, at least if you look at this reagent, you need to figure out, oh, that looks like a Martin reagent. For iodine and the reagent, Martin can stop the oxidation at the stage of aldehyde. Okay. That's what we just studied. If you wanted to make carboxyl acid, then you can use a stronger oxidizing agent, like a CR3, formaldehyde, kind of a strong antioxidizing agent you can push to the end. How will you achieve this? Ester, and you wanted to make it into the aldehyde. From ester, we have learned some reactions. What reagent have we used? Here it seems like there is no further alkyl involved here, only the hydride and the hydrogen is involved here. Okay? Then hydride reagent, you have learned two things: sodium borohydride and the lithium borohydride, lithium aluminum hydride. Sodium borohydride you added here, what happens? No reaction. That's mild reagent, and it can react with only aldehyde and ketone, and it generates the alcohol. Lithium aluminum hydride, if you add there, what happens? It makes alcohol. Then here, if you add that kind of reagent, even though this may be formed as an intermediate, this one is more reactive than this for the reduction. Then it may not stop here, it may go further, even with the sodium borohydride. So you need something special in this case. That reagent people have developed, so-called dibar, or when I learned that, they call it dibar, because it has aluminum here. Dibar H or dibar with a different name, but with a bulky group here, as you can see here, this is stronger than boron. So it's similar to lithium aluminum hydride, but with a very bulky groups around. So it has some selectivity with a steric hindrance. And this reagent has been developed to show that starting from ester, it can start with reactions at the stage of aldehyde. Very useful reagent. So to make this, of course, the chemists have tried to make tens of, maybe hundreds of different derivatives. And then finally they picked up the best one with bulky, the butyl group, second butyl group, and then aldehyde at the end. And also not Al minus, this Al 0, as to reduce the reactivity from lithium aluminum hydride. Lithium aluminum hydride case Al minus. So that kind of other reagent as you may be here, so-called dibar, following your textbook. Very unique one. Similar thing we have studied the learned N-succinylidine and bromosuccinylidine, NBS, which could provide the bromine to the benzene site. That kind of reagent, case by case, that was a big discovery. So even though you do not understand fully the mechanism, still it will be very useful on the reagent. Okay, this one, alcohol to ketone. Easy. Any kind of a strong oxidizing reagent. Chromate reagent, permanganate, any kind of strong oxidizing reagent. It cannot go further, so it stops there. If it is aldehyde, then it can go further to the carboxyl acid. And this reaction is quite popular and useful, and maybe you have already learned, I'm not sure, in the organic chemistry one. Have you learned about ozonolysis? If you add ozone onto double bond, it forms intermediate. The ozone is a 3 oxygen, it forms this kind of intermediate, and it goes for rearrangement. Depending on those workup reaction, it could be done oxidatively or reductively. Okay? If you look at those reagents, this reagent, is that reduction condition or oxidation condition? Zinc powder, oxidation or reduction? Metal powder, that should be reduction. Right? Metals, they provide electron they becomes metal cation. Metal powders are reducing agent. Provide electrons. Right? It's different from aluminum chloride. That's with the acid. It's already provided and different efficient state. But metal powders, they have still electron to dominate permanently. That's the reducing agent. So with the reducing conditions, it is added here and oxygen is added in each position, but in the reduced form. If you add oxidizing recovery up here, then ketone is the same. But the other side, you have carboxylic acid, forming acid, not forming the formaldehyde. Okay? Only the workup part is different. Ozonolysis, you add oxygen in between and clip and donate double bond, CO double bond here and CO double bond there. And finishing up either oxidatively or reductively. 해내줄 되고 어디가 있으면 안 돼요. Okay, this reaction we have learned. What is the name of this reaction? Friedel-Crafts oscillation. Right? So we just have learned this. And the result is it generated ketone. That's why it just showed as an example. If you use alkyl group here, alkyl chloride, we will get just the alkyl added to the product. Right? That's not carbonate added, but it's a series of reactions we have done as a part of electrophilic substitution. Right? With the acid catalyst and alkyl halide or acyl halide. Okay, this was the preparation. CO double bond starting from alcohol and oxidizing, or from ester, remove those alkoxide and then generate the aldehyde using special reagent Dival. And ozonolysis is another way, and oxidation in general, strong oxidizing reagent. So always tricky part is how to start the reaction at the stage of aldehyde. That was a little tricky. Aldehyde is always more reactive than ketone, then the ester. Now reactions. If you have aldehyde and you add further oxidizing reagent, this should be easy. What product do you expect? 그렇게 준영아. 생각하지 말고 빨리 쉬운 문제들. Aldehyde, if you further oxidize, it forms carboxylic acid. The perchromate, permanganate, and the strong oxidizing reagent. So this is the end of the position. Now, if you look at the reaction, it seems like it's aldehyde here and oxygen is inserted in between. Seems like. So aldehyde can go further to generate carboxylic acid. Ketone cannot, because this one cannot be inserted here. But if you look at the mechanism more carefully, it seems like there is some other intermediate. This bracket means this is intermediate. Now this kind of reaction happens with water. Water seems like the added. Now this carbon was sp2. sp2 means it's the planar, 120-degree planar structure. And once this water is added here, then this hydrate product. Hydrate means water. Carbohydrate. Carbon plus water. That's a carbohydrate. Okay. Now this hydrate product is sp3, and this has tetrahedral structure. And it seems like through this kind of intermediate, and then oxidation happens. Seems like taking up this electron here, this proton here, and then by depriving this electron and push it out and then remove this and then oxidize it. And this one is reduced and then this product is oxidized. Now we started to look at this kind of hydrate addition, so-called nucleophilic addition. So far we have drawn, if this water is added through here, always we have drawn that arrow. 지금부터 중요한 얘기하니까 잠깐 저기 친구들도 다 돌아와. always when you had this carbonyl group, you already have seen any kind of a nucleophile, like here, sometimes we draw nucleophile here or draw like this. This arrow means this is a 2 electron moving, right? 1 electron moving is this is 1 electron moving. Okay? 1 electron involved, that involves radical as in the reaction mechanism. 2 electron movement is general electron are the base the chemistry happens. We draw like this or sometimes we draw like this. It implies that maybe on this plane and it's coming from the same plane it comes in. But always if you think about acceptive reactions, electron orbital overlapping is very important. Of nucleophile coming in and the leaving group's direction should be on the same line. Then orbital overlapping is maximized. Coming in and then that electron wave movement push out and the leaving group leaves here. That's why it should be exactly on the same line. Then reaction speed is maximized. That's why stereochemistry conversion happens through this planar intermediate, not intermediate, transient state, and then push it in, and then this envelope, the umbrella is converted to the other side. Here, this reaction also similar orbital overlapping is very important. Here, the orbital is apparent orbital is phi orbital here. And this phi orbital's orientation is if this is on the same plane, this should be phi electrons like this. Then to match that electron overlap, nucleophile cannot come through here. Then this is perpendicular to each other. Right? If this kind of orbital perpendicular relationship, what do you call it? If an orbital is perpendicular direction, that's why there's no practical overlapping. Its end result is a non-bonding, but that perpendicular, that's why no effective overlapping. There is some special term. They are 못 들어봤어? 1학년 때 들어봤을 때 퀀텀 메케닉스에서 몰레큘러 오비탈을 배우고 할 때 들어봤을 텐데 수학적인 term인데 원래 서로가 직교한다는 뜻이고 orthogonal 혹은 orthogonality 직교성이라고 하는 것이 여기서도 밥에서도 이 오비탈이 정확하게 딱 매칭이 되지 않으면 완전히 90도로 만나면 인터랙션이 일어나잖아요. 인터랙션이 상쇄되게 되죠. So, if the nucleophile is approaching from this plane, reaction doesn't happen. That's why the real reaction happens. Nucleophile is approached to the direction of phi electron. If that is fully perpendicular, it should be 90 degree. But if it is 90 degree, then it cannot push this electron to the behind. That's why a little tricky. But 75 degree is quite stiff, right? If this is like the SPC here, then this is 90 degree, 75 degrees about this. Push this reaction from one side. That phi electron is pushed, and where does it go? It goes through behind here, which carries this oxygen carries that electron behind there. That is the direction of the addition of nucleophile to carbonyl group. This figure is very important. With this, the idea and concept, then we can decide the stereochemistry, what's going on the chemistry of a carbonyl site. Okay. Carbonyl, in comparison to CC double bond, it has electrons shifted to oxygen side. That's why this carbon position becomes electrophilic. That attract the nucleophile means attract electrons, and then that electron comes through that 5 electrons reactions. And then this 5 electron is pushed and then move behind of this oxygen position. Okay? As the result, it forms this kind of a tetrahedral intermediate. And if it comes back, then that pushed electron, we push it back and comes back and then remove something. That can be one possibility. That's almost similar to reversible reaction of SN2 reactions. Nucleophile goes in, living group is almost left, but living group can come and then reverse this reaction. Then that's in equilibrium. That reaction also can happen on this carbonyl too. But if it does not happen, then once it is pushed, then the reaction finished. The reaction is finished by protonation deposition. Then this is product. Now, with a different kind of nucleophiles, especially if it is a negatively charged nucleophile, then it tends to finish at the end by giving that the nucleophile protonate and finish. But if that is neutral, the nucleophile, then nucleophilicity is maybe lower than this. And then there is a chance of reversible reactions in equilibrium. We see some examples. Now, if we compare the reactivity of aldehyde and ketone, this reactivity means reactivity to nucleophiles. Now, nucleophile needed to come in, 5 electron is here, and then one way is aldehyde versus the ketone. Steric hindrance wise, aldehyde is much more open than ketone. So steric hindrance wise, aldehyde is more reactive, makes sense. This is similar to nucleophilic. This is nucleophilic addition. Nucleophilic addition is very sensitive to steric hindrance, right? That's why if it attacks here, around the environment, around this carbon center is quite important. Now aldehyde is less hindrance, has less hindrance than ketone. That's why aldehyde is more reactive. Sterically. Electronically, what do you think? Electronically, the difference is aldehyde has one hydrogen, ketone has extra alkyl group. Alkyl versus a hydrogen, which is more electron donating. Alkyl is more electron donating. If more electron donating, then reactivity wise, that would be more reactive or less reactive. Because that position is more stabilized, means these partial positive charges is the driving force of attracting nucleophile. Because this electron is pushed to oxygen side, that's why this becomes electrophilic. If it has more electron donating group, then that tendency is reduced. That's why electronically also aldehyde is more reactive than ketone. Now let's think about this analysis, what we have learned from carbocation formations. In the last semester, we have learned about the carbocation formation as an intermediate for E1 or SN1. And we said primary carbocation versus secondary carbocation. Secondary carbocation is more stabilized because of this electron donating effect. And that's why product-wise, E1 is more preferred for the secondary or tertiary because it's more stabilized. Wait a second. Now we are saying opposite effect. In this case, with more alkyl group, there is more favorite. And now we are talking about with more electron donating here, stabilizing is a similar effect. But we are saying reaction is more preferred this way, not this way. What's the problem here? Why the conclusion is different? Say again. Oxygen. Oxygen has withdrawing effect, so 그 말이 틀린 말은 아닌데 왜 이 반응이 이쪽에서는 이 반응이 더 선호되었고 여기서는 이 반응이 더 선호되었는지에 대한 직접적인 설명은 아닙니다. In both cases, this one is more stabilized. True. This one is more stabilized. Same. But reaction-wise, this was more preferred to go to the next step. We usually get the product from here, but in this case, the product is formed from here. What's the explanation? 여러분이 답할 수 있는 수준이십니다. 아주 세련되게 답을 한 건 아닌데 키 포인트는 짚어서 얘기했어요. In this case, forming this carbocation as an intermediate is the rate determining step. Whether we can form this or not, that is important. This should be formed, then it can go to the next step reaction. Okay. That's why more stable is important to be formed. But in this case, this is the reaction of the rate determining step is from now on here, whether it can go to next step or not. Okay. So in that case, more reactable one can go to the next step. In E1 or SN1 mechanism, the next step of adding, nucleophile here or elimination, that reaction is too fast. So that does not bother the reaction rate. Rate determining is determined by the forming of this key intermediate. That is the difference. Okay? Now, based on this analysis, benzaldehyde comparing to other alkyl acetaldehyde, which one may be more reactive? Benzaldehyde and acetaldehyde. Allyl group's electron donating effect compared to alkyl group, what do you think? 시작할 때 퀴즈 풀면서 배우잖아요. Allyl group has electron donating effect, maybe stronger than alkyl. Then reactivity-wise, benzaldehyde is more stabilized than general aldehyde, alkyl aldehyde. So benzaldehyde, in your textbook, there's a bunch of this explanation like this. But simply speaking, there are more electron donating effect, more stabilizing that carbon center. So reactivity drops. Makes sense, right? A little less stable means that's more reactive. If you stabilize that reagent too much, then starting materials are too much stabilized, activation barrier is becoming bigger. Okay, let's focus on hydration. Adding water molecule to carbonyl group. Water molecule to ketone or aldehyde. Now water can be nucleophile, weak nucleophile, but still this oxygen has a lone pair electron. Can attack here, but now you should imagine from now on, not from the bottom like this, it goes like this, okay? Goes like this, and then push out the electron behind here. Then the product is formed like this. This kind of hydrated product, usually, as we draw, even though we put acetone in water, we don't want to think like this way. Majority of them is still acetone side, ketone side is more dominant. That's why usually, even in water, acetone in water, usually we use this for what? acetone 물 탄 거 어디 쓰죠? 면역기 줄 때 남학생들 잘 모르지 몰라. Here, still the majority form over here is more than 99% acetone form. But some cases, like a formaldehyde, now sometimes this hydrated form is much more dominant. Then, if you add this into this solution, so-called formalin, 박물관에서 샘플을 오래 보관할 때 formalin 물에 넣으면 이게 뭐죠? 그럼 이렇게 그리는 게 fe어야 할까? 이렇게 그리는 게 사실은 더 맞지 않는다. Then we should think always which is the equilibrium wise, which is more favored, this way or that way. That's something we need to think. This is in dynamic equilibrium. Now the mechanism, water is attacked here. Base condition, acidic condition, both ways is possible. Base condition, nucleophile is OH minus. Attack again, same angle, 75 degree, push this back behind, and then protonate and finish. Still, this reaction can be reversible. Acidic conditions, then there is no OH minus. Water is nucleophile, but activating part is this protonation on oxygen. Then that becomes more electron poor, then attract this weak nucleophile. Attack, and then product seems like a similar, but equilibrium-wise, when this side is more equilibrium than base conditions, because of this weak nucleophile and protonation effect. That's why this kind of acidic environment and reagent, usually equilibrium is moving on, but this is more preferred usually than the product, because this one, this guy is Br minus, Cl minus, these are stable enough as a reagent, and nucleophilicity is not so strong. That's why usually this is more preferred, just it, than the hydrated form. But sometimes we can push that equilibrium to the added form. One of the examples is using nucleophile cyanide. Cyanide is quite unique carbon nucleophile. Cn minus and these negative charges on carbon has a good nucleophilicity. If this is added to carbonyl, then it can form this kind of intermediate and protonate. And relatively, this one is a quite stable product. Cyanohydrin product is formed as quite stable and useful reagent. And why that is useful? Once you make that reagent, starting from the carbonyl like aldehyde, add Cn minus, Cn is added here. You can do two reactions, two different kinds of reactions. You can reduce this or you can hydrolyze this. Now let's check. If you add Cn here, if you reduce, what product do you expect? Cn triple bond is reduced with a lithium aluminum hydride reagent. Let's review. If you have a CC double bond, to reduce this, what kind of catalyst and what kind of reagent that we used? CC double bond into CC single bond. Say again? 좀 크게 얘기해 줘. 누가 하겠어? H2 hydrogenation using what kind of catalyst? Like a palladium or platinum kind of reagent you have used, right? In that case, there is a non-polar reagent. Non-polar are the substrate. But lithium aluminum hydride, this is a polar hydride that prefers to attack polar site, like a carbon. So if you add CC double bond, lithium aluminum hydride or sodium borohydride, reaction doesn't happen. But that attacks carbonyl and to make the alcohol. That's what we have learned. Right? Similar things can happen. That's not CO, but this is Cn. Cn is also polarized. Electron is shifted to this direction. Hydride can attack this position. One reaction finished, there's still double bond there. Another pair of 5 electrons. It can attack again. Then what's your end product? It can form amine. Cn double bond and amine. Okay? You can get this kind of product. Organic chemistry wise, this is a quite useful reaction because it forms neo carbon-carbon bond. Organic molecules backbone is carbons. Extending carbon to the other carbon is most important reaction in a sense. So here, by adding cyanide, we can effectively introduce one carbon extension. And then, doing this chemistry reduction, we can make this into an amine product. Now, if you add acid and heat very vigorous conditions, then you can hydrolyze this. Cn triple bond, in a sense, it has some similar property of a CO double bond. Then by adding water and acid condition, you can hydrolyze this and then push out, and then remove this end. Instead of that, introduce water. You can generate the carboxylic acid. Okay. This kind of reactions we'll study 2-3 weeks later for the carboxylic acid the reactions. But here, kind of an intro, utilizing the CCN. If you hydrolyze, then you can generate carboxylic acid. So because of this useful the derivitization, this CN addition reaction is quite useful. How about this? This is DB. We already have one. Aldehyde, sodium borohydride. What's your product? Alcohol, primary, secondary, tertiary. Primary alcohol we can get. If you have ketone and then sodium borohydride. Secondary aldehyde, secondary alcohol we can generate. Here, the nucleophile is a hydride. We didn't touch this part, but again, this is a nucleophile, and then it is added like this. Now, we use this kind of error drawing, but now, practically, in reality, hydride attacked from here, 75-degree angle, attack there. Similar situations. Hydride is also nucleophile. Okay? Similar reactions we have studied with the Grignard reagent. Rather than hydride reagent, alkyl anion, similar reactions we can expect. Rather than hydrogen added, alkyl is added. Then primary the aldehyde, you use Grignard reagent product. Primary alcohol, secondary alcohol, because alkyl is added. If it is a ketone, then Grignard reagent, tertiary alcohol we get. So this is we have learned already, but now mechanism-wise, addition to the carbonyl is kind of the reaction. We just learned with this angle, but now we review and check with our previous knowledges. Now reaction-wise, this is metal, and then alkyl halide, and metal side can react as metal ion, metal cation, act as Lewis acid, like aluminum chloride. Similar situation with the lithium, the alkyl, same way. Lithium plus is act as Lewis acid. And then R minus attack here, 75-degree metal. Okay. And then tetrahedral intermediate, and then protonation here, finish up the reactions. Now a little different the concept of the imine and enamine. Addition to the carbonyl group, there can be anionic nucleophile or neutral nucleophile like water. Anionic one, add it and then just finish up by protonation, which is the best of the product, like Grignard reagent or hydride reagent kind of case. If it is a neutral one, now rather than this is protonated here, dehydration also can happen. Elimination. This one is added, nucleophile is added, and then this OH and this was neutral originally, now it becomes partly charged, and then this proton and water is combined together and removed. That's what we call elimination. Right? In E1, E2, we have the same thing. This reaction is also possible. And make double bond not with the oxygen, it make double bond with the nucleophile. Looks like a little complicated, but real example is simple. Now here we have ketone or aldehyde like this. And then one option is with a primary amine, and the other one is with a secondary amine. With a primary amine, it forms this product. And the result wise, amine will nucleophilically attack here. Right? The intermediate will be amine added here, and then CO, the CO single bond, and O minus here. And then protonate, then that should be end product. But in a sense, that's similar to hydrate the product easily. Carbonyl, and then water attack, and 2-hydroxyl. That one is usually not stable, as we have seen in acetone. Usually they go back by losing one water. It's similar reactions here. Rather than water, amine is added there. If you look at the mechanism, amine is added there. Then OH and amine is making this kind of tetrahedral structure. It's similar to OH situations. Usually it's not stable. Then they choose either they remove or going back. This electron comes back and pushes this out. Then this is reversible reaction. Go back to the starting state. Rather than that, this nitrogen also has this lone pair electron. It pushes out like that and then pushes this out. They are competing. And reaction-wise, especially in dehydration conditions, by removing water, then amine is slowly take up that position, and CO double bond, that oxygen is replaced with the CN double bond. That's the result of forming this product, CN double bond. This CN double bond product we call imine. Amine was a CN single bond, right? CO single bond we call alcohol or ether. CN the CO double bond we call carbonyl, aldehyde ketone. CN single bond amine. CN double bond like this. This is what we call imine. Okay. So by adding amine, it can replace the CO double bond oxygen with plasma. Now, if you add, interestingly, secondary amine, now it forms a little funny product like this. It could be CN double bond here, but that double bond, problem is that double bond forms this kind of charged species. Previous case, there was a proton, and proton could be removed by with positive charges. But in this case, this is secondary amine. Now this positive charge cannot be removed. So they choose, there is no proton here, they remove this proton here. And then it forms like this. This is a very similar situation of we already have a lung. We have learned this kind of situation. Right? This is a ketone form. This was an enol form, in oil form. Right? Very similar way, it forms here. In is formed, and then amine is generated here. So enol and amine. So this form we call enamine, and the other form could be imine form. What is the relationship between these two? Imine and enamine. 하나는 지난번 맞췄으니까 답하시면 tautomerization. There is a tautomer. Only proton is shifted from one side to the other position. There is a tautomerization. Okay. So to summarize these reactions, if aldehyde ketone is reacted with amine, especially with the dehydrating condition, if you remove the water, then water is removed and oxygen is replaced by amine. And it can form ketone form. Ketone form we call imine. Enol form we call in amine version enamine. Imine is formed with the primary amine, and enamine is formed with the more preferably with the secondary amine. Okay. Oxygen was replaced with nitrogen. 그렇게 생각하면 좀 더 쉽겠지. This kind of the bond is the commonly found in nature. So in the biological systems, if there is any aldehyde and free amine, then they can react and they can form this kind of imine form. Imine form discovered by this chemist, Stafford Schiff. So he named this kind of a structure Schiff base. Amine is a basic. So even it forms this kind of exchange reaction, still it has a basic property. So it's called the Schiff base. Okay. And what do you think? That imine product usually reversible reactions. If you add more water, then water amount is higher, then equilibrium can be shifted to ketone form. Makes sense, right? You add amine, remove water, then oxygen is replaced with a nitrogen, that's imine. Now there, if you add water, then equilibrium can be shifted to the back. Amine is kicked out, and water replaces that, then ketone is recovered. Okay? So that is a kind of reversible reaction. Now, if you add this reagent, similar to amine, but with one more heteroatom. In this case, this reagent is called hydroxylamine. NH2, NH2, it has a different name. Anybody knows? Later. Hydroxyamine, if it forms, then rather than hydroxylamine attack this position, replace this and then forms this kind of imine-like structure. CO double bond is exchanged to the CN double bond. With the help of this extra heteroatom, this product is quite stable. Can be easily crystallized too. We may be forming hydrogen bond here. So this product is called as oxime. Hydroxylamine added to carbonyl group, we can form stable oxime. And this similar reagents with NH2 not OH, NH2 or NH alkyl. This reagent is called as a hydrazine. And hydrazine is added, similar effect. It can form CO double bond is exchanged with the CN double bond, and this product is also stable. And name-wise, this product is called, this structure is called as hydrazone. Ketone, just amine, imine, with a hydrazine added hydrazone, and hydroxylamine product is oxygen. These guys are forming stable product, so it's almost finishing up. The equilibrium is fully shifted, so it doesn't have another arrow, right? If it's equilibrium, you may go this way and small amount this way. But in this case, almost one direction, moving to that direction. This is kind of a stable imine formation. And these reactions requires both protonation and deprotonation. That's why this reaction has optimum at the pH around 4 5. So weak acid condition is preferred to imine formation, hydrogen formation, or oxygen formations. Weak acid conditions. Okay, to summarize. With this ketone, you add this one and this one. What product do you expect? Upper one, it forms imine. This one, secondary amine, it forms the enamine. Okay, so this is a summary of this. Okay, up to here, we finish today's lecture. We just studied about the carbonyl reagent